Welcome to the final presentation of ME Team 71, the Autonomous Aerial Inspection of Wind Turbines, sponsored by the Naval Undersea Warfare Center, or NUIC. The team is composed of Dylan Stadmeyer and Aryaman Misra, advised by Professor Liko Trafidis. This project presents the research, design, and development of an autonomous aerial unit capable of utilizing computer vision methods for the inspection of wind turbines. This is the first step in fully automating the inspection procedure. The object detection model will be deemed proficient if it recognizes horizontal axis wind turbines as a whole from a distance in various angles, lighting environments, and physical environments. Additionally, the model must recognize three main components of a turbine, including three primary rotor blades, the central hub, and the turbine tower under those same conditions. A model accuracy of 95% and a 250 millisecond or 4 frame per second model latency are the two main performance goals so that it may be used in real-time scenarios. The outfitted drone will successfully receive input in the form of video and send output to the drone user for piloting and analytical purposes. The team's initial approach to reach these deliverables was to explore environments capable of either creating or retraining an existing object detection model, examine what components and performance requirements were needed to successfully construct a complete input-output feed, and find a drone capable of lifting the payload created by the onboard components. Based on both resources and time, the team decided that retraining a state-of-the-art detection model was more feasible than creating one from scratch. Generally, creating a successful detection model requires tens of thousands, if not hundreds of thousands, of images for each class. The final model chosen to retrain and run the input feed into was the single-shot detection efficient object detection model. The model was initially trained to recognize 90 classes of everyday objects, and the team retrained the model with a custom data set to recognize the wind turbine and three auxiliary components.
To select the components necessary to acquire input data and send it to the pilot, compatibility was the most important criteria. For this reason, a Raspberry Pi was chosen. A discrete battery supply was also included. In order to minimize transmission delay, a Raspberry Pi camera was chosen. A receiving device capable of processing information from the Pi was needed, and a mobile device with a cellular hotspot was a perfect candidate. An SD card was included to store field videos and images, and a wireless adapter capable of increasing the communication distance to a maximum of 250 meters was included. The onboard components were integrated on top of the X500 drone. The Pixhawk 4 Mini flight controller was selected for its advanced features such as capability of planning flight routes and automation. A broad range of flight functions were made available to choose from on the RC transmitter, such as hover, stabilize, and return home. A common saying in the machine learning community is that a neural network is only as good as the input data. In order to train an adequate model, several thousand images need to be used. However, due to the lack of distinct images, the input data were prepared using methods of data augmentation. This would yield increased accuracy and robustness in the model. A script was designed to produce new images to train the model by rotating, horizontally flipping, adding noise, changing the color, and adding blur to the original images.
The final training iteration of the detection model utilized the newly created custom training dataset of approximately 1,000 512 by 512 sized images containing anywhere between 800 to 1,200 instances of each class. Different parameters such as batch size, learning rate, and maximum detection boxes drawn were tweaked within the model until optimal results were attained. In this case, the reduction of the total loss of the detection model was the goal. The total loss for the final iteration of this model was roughly 0.3. The results of the retrained model are seen through inferenced images from the testing dataset. The model accuracy for the whole wind turbine class produced fairly accurate results, with the testing dataset varying anywhere from 80 to 98% accuracy. The auxiliary classes showed less accuracy, as in general, these components are smaller portions of the input image in comparison to the wind turbine as a whole, therefore less information is available to inference due to their size. A major finding from these results was understanding the computational limits of the Raspberry Pi microcomputer. With the final model iteration, the Raspberry Pi inferenced live video feeds at roughly 0.5 frames per second. Numerous methods were attempted to optimize the model, including converting the TensorFlow model to a TF-Lite model format, but the accuracy was severely degraded in return for a minimally faster runtime of around 2 frames per second. To visualize what a real-time inference video feed would look like, the team inferenced individual frames of sample videos of wind turbines and converted them back to video format as seen here.
Once the drone construction was completed, multiple flight tests were performed using a manual flight mode to test the flight capabilities of the entire setup. The Pixhawk Mini flight controller was initialized successfully and configured to log flight details, and multiple flight modes were added, such as hover, stabilize, and land, in order for smoother functioning on the pilot's end. To date, a custom dataset comprising of over 1,000 wind turbine images has been created in order to train the model. The Efficient model was modified to recognize a wind turbine and its constituent components as individual classes. While the 4 frames per second goal was not reached due to practical hardware constraints on the Pi, the Google Coral TPU offers additional hardware used for machine learning models, which can provide the Pi the necessary computing power to run the model at a faster frame rate. Further steps include additional training on the model for new and augmented images for each class. On the drone front, the construction of the X500 was completed and the onboard components were integrated. The team also observed that in order to optimize flight time, a smaller battery could be used to power the Pi as long as the output current was no less than 2 amps. On the future automation front, Q ground control could be used in conjunction with the Pixhawk 4 Mini, allowing for automatic pre-planned flight routes with functions such as survey, stabilize, and hover, making the process entirely autonomous and less prone to errors.